let's do some ray tracing for mirrors now. Mirror practice number 1. And I just wanted to clarify, if your real rays are converging, whether it be a lens or a mirror, based on the lens. If it's converging, you're going to use the left focal point. If it's a diverging lens or a diverging mirror, you're going to use the rightward focal point. I just want to kind of clarify that a little bit. So a convex lens is converging, and a concave lens is diverging. And I'll draw that too. So a convex lens is converging regardless of where the rays are coming from. They're still converging even if they don't converge at some point. It's still a converging lens. And the same is true of a mirror, because if the light waves come in, they're still going to come together. And the opposite is true of lenses, or I'm sorry. Okay, so my lenses are on the top and my mirrors are on the bottom. The opposite is true for diverging. So if your rays come into a lens, it's going to diverge for a concave lens. And if you have a convex mirror, your rays are going to basically scatter. And that's what I was talking about before with scattering. Scattering, you use the behind focal point. Converging, you use the leftward focal point. Oh, I didn't finish writing this problem. All right, a 10 centimeter tall candle is burning 60 centimeters away from a concave mirror. With focal length 20 centimeters. Any other important information? That's it. So number 1, of course, what's the image distance? Number 2, real or virtual. Number 3, upright or inverted. And 4, magnification. Magnification. All right. As always, start with a crude diagram. We have a concave mirror, focal point here, and the person is further away than the focal point. I'm sorry, the candle is further away than the focal point. So from the top of the candle, I'm going to draw my 3 rays. It's going to hit there, bounce to the focal point. Number 2 is through the focal point and back parallel. And number 3 is through the center of curvature and back. And it's a converging mirror, which means we're going to use the leftward focal point. Okay, so I have a rough idea. I know that it's going to be inverted. And because this is where the actual mirror rays are going to be for where our rays converge, I know it's going to be a real image. That's what you would expect. You would expect a mirror, the image to be on the left-hand side. That's how mirrors are supposed to be. And when it's the way it's supposed to be, that means it's going to be a real image. And we just established, based on my crude drawing, it's going to be inverted. So now let's get to the meat and potatoes of the problem. Start by drawing it, and we're going to add our principal axis. Um, 60 centimeters away, and I'm going to use a scale of half, so I'm only going to mark it about 30 centimeters away. And the focal length is 20, so I'm gonna mark that 10 centimeters away. And I'm gonna put it on both sides as always. Focal point, candle. Ooh, how tall is my candle? 10 centimeters tall, and I'm using a scale of 10. 10? What was my scale? Oh, my scale is completely out of whack. No, I used a scale of a half. So instead of 10 centimeters tall, candle's going to be 5 centimeters tall. So there's the top of my candle. There we go. Which focal point are we going to use? It's a converging mirror. Converging lens and mirrors mean you use the left focal point. So that's the focal point I'm going to use for rule number 2. But I'm jumping the pony, horse, whatever it is, and I'm going to go back to rule number 1. And I'm going to draw parallel to the principal axis. And I should have drawn a dotted line right through the middle of that sucker, and then back through the focal point. Yeah, that's pretty good. Rule number 2 is through the focal point, just like I asked. Which focal point are we going to use? Yeah, the left one. Why? Yes, converging. Good. No, that's not a fun arrow. Oh boy. That's tight. Okay. And number 3 is through the center of curvature. And I'm going to try to come back out at that exact same angle. And yeah, I'm cheating and just going through where my other axes are. And look at that, it went right through. And that's where my rays are going to converge. Oftentimes you only need 2 rays to know exactly where your image is going to appear, but it's not a bad idea to draw the third just to make sure you did the first 2 correctly. And there's my candle. Oh, it's a tiny little candle. So I'm guessing my magnification is going to be less than 1 because it's smaller than the actual object. But we'll calculate that to make sure. It's inverted, that's exactly as we expected. It's a real image. And now let's do some math. 1 over SI equals plus 1 over S naught. No, SO. That's not a naught, that's an O for object, equals 1 over the focal length. Oh, I didn't measure. It's 17 centimeters apart. So based on my scale of 2, that would mean the image distance is going to be roughly 34 centimeters, hopefully. And my magnification, it appears to be about 2.5 centimeters tall. So my image height will be roughly double that based on my scale of 2. So I'm hoping it's going to be 5 centimeters-ish. So that's what we're hoping for. I hope I said image height, not object height. You know what I'm trying to say. 1 over SI, the image distance, that's what we're trying to calculate, equals 1 over the focal length, 1 over 20 centimeters, plus 1 over, bringing this to the other side means it's going to be subtracted from both sides, and it's 60 centimeters away. 60 centimeters, 1/20th minus a 60th is 2/60ths, which is a 30th. 3.33. That makes sense. We got 34. Not bad. Not my best work, but pretty good. So the image distance is 30 centimeters. And based on our scaling, that's pretty decent. All right, let's find the magnification. Absolute value of image height over object. I'm sorry, image distance over object distance. And if you're ever trying to remember this equation just for the sake of memorizing it, remember the old children's game. Hi ho cheerio, si so serio. Da, 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 da. 30 divided by 60. Oh, that's exactly half. Which is exactly like we intuitively thought about. It's got to be less than 1 since it's a tiny little image. And half of our original object height. Bling bling. Magnification is a half. Magnification times object height equals image height. Magnification was 0.5 mathematically, times the image height, 10 centimeters, equals 5 centimeters. Exactly like we graphically interpreted. Cha-ching. Thanks.